Light is not the fastest thing in the universe. This single idea shatters our cosmic expectations. As physicist Arthur Eddington once noted, the speed of light is not merely a speed limit, it is a fundamental property of spacetime itself. By the end of this exploration, you will understand the real physics behind faster-than-light communication and why it remains one of science's most compelling frontiers. We will uncover whether spooky quantum connections can truly send messages and if cosmic shortcuts through warped space are even possible. What does it truly mean to send a signal across the void? Think of spacetime as a vast cosmic fabric, a highway where light itself sets the ultimate speed limit. This is not a suggestion, but a fundamental rule woven into the universe's very structure, first articulated by Albert Einstein in his special theory of relativity. The principle is deceptively simple. Nothing with mass can ever reach the speed of light in a vacuum, and nothing, not even massless particles or information, can exceed it. This speed, approximately 299,792,458 meters per second, is the universe's ultimate constant. Its origins lie in the elegant yet profound realization that the laws of physics are the same for all observers moving at constant velocity. This symmetry leads to an inescapable conclusion. As an object moves faster, its mass effectively increases, requiring ever more energy to accelerate further. To actually reach the speed of light would demand an infinite amount of energy, a clear impossibility. Physicists have tested this rule relentlessly, from particle accelerators like the Large Hadron Collider, where protons are pushed to 99.9999991% of light speed but never beyond, to observations of cosmic rays from distant galaxies. This speed limit is not just about motion, it is the guardian of causality itself, the logical flow where causes must always precede effects. It ensures that the sequence of events remains consistent for everyone, everywhere. This is enforced by two strange consequences of relativity: time dilation and length contraction. As you move faster, time itself slows down for you relative to a stationary observer, and distances in the direction of your travel appear to shrink. These effects are not illusions. They are measurable realities that adjust the very fabric of reality to prevent any violation of the cosmic speed limit. So what happens if we could somehow break this rule? The most immediate casualty would be our understanding of reality. Cause and effect would unravel. An effect could theoretically happen before its cause, creating paradoxes that defy logic. You could receive a message before it was ever sent. This foundational rule, so rigorously defended by nature, forces us to ask a deeper question. Are there any backdoors, any theoretical loopholes in spacetime's architecture that could allow a message to cheat this universal law? Even Albert Einstein was unsettled by one particular implication of quantum theory, calling it spooky action at a distance. This was his famous reaction to the Einstein-Podolsky-Rosen paradox, a thought experiment designed to highlight what he saw as a deep flaw in quantum mechanics. The paradox centers on a phenomenon we now call quantum entanglement, where two particles become inextricably linked, their fates intertwined no matter how far apart they travel in the universe. Measure one, and you instantly know the state of its partner. This connection seems to defy our classical understanding of space and separation, presenting a puzzle that baffled its own discoverers. As contemporary quantum physicist Dr. Nicole Unger-Halpern notes, entanglement forces us to confront the fact that the universe might be fundamentally interconnected in ways that challenge our most basic intuitions. So how does this spooky link actually work? Imagine two magical dice created together in a special way. You take them to opposite sides of the galaxy. When you roll one die and it shows a 3, you know with absolute certainty that the other die at that very instant also shows a 3. The outcome was not predetermined, it was created by the act of measurement itself. This is the essence of entanglement. In laboratories today, scientists create entangled pairs, often using photons of light. By carefully manipulating certain crystal structures, they can generate two photons whose properties, like their polarization, are linked. Once they fly apart, any measurement performed on one photon will be perfectly correlated with a measurement on the other. This is not just a theoretical curiosity, it forms the basis for ultra-secure quantum cryptography. In quantum key distribution, any attempt to eavesdrop on an encrypted message disturbs the delicate entangled state, immediately alerting the communicating parties to the presence of an intruder. It feels like the perfect setup for instantaneous, faster-than-light communication. Just manipulate one particle here, and your partner light years away sees the change instantly. But here lies the profound catch that prevents this spooky link from breaking the cosmic speed limit. While the correlation is instantaneous, the actual outcome of each measurement is completely random and cannot be controlled. You cannot force your die to land on a specific number to send a pre-arranged message. The universe, it seems, allows for this strange, intimate connection, but cleverly prevents us from using it to send a single bit of meaningful, controllable information faster than light. So if this quantum channel is closed, where else can we look for a loophole in Einstein's cosmic rulebook? Two scientists, separated by a vast laboratory, believe they have found the ultimate communication system. Each holds one half of an entangled photon pair, a spooky connection spanning the distance between them. One scientist, let us call her Alice, tries to send a simple binary message to her partner Bob, a single yes or no. She decides that if she measures her photon and finds it polarized vertically, that will mean yes. She performs the measurement. Instantly, miles away, Bob's photon snaps into a correlated state. The problem is, Bob has no idea what that state means. When he measures his own photon, he gets a result, but it is completely random. He sees a vertical polarization. Was that a yes from Alice, or was it just a 50-50 chance outcome? He cannot tell. This is the core of the no communication theorem, a powerful rule in quantum information theory that acts as a cosmic referee, ensuring the speed of light is never broken. The pioneering physicist John Stuart Bell's work in the 1960s helped formalize the boundaries of these quantum correlations, showing that while the connection is real, it is fundamentally useless for sending a controllable signal. The proof of this theorem is both subtle and elegant. It demonstrates that no matter what operation Alice performs on her particle, the statistics of the results Bob can possibly see on his side remain entirely unchanged. From Bob's perspective, his particle behaves exactly as if Alice had done nothing at all. His measurements are always a coin toss, completely independent of Alice's actions. The only way for them to discover the eerie correlation is to later get on a classical, slower-than-light channel, like a radio or fiber optic line, and compare their lists of random results. It is only in that comparison after the fact that they can see their dice rolls were mysteriously matched. Without that ordinary communication to establish context, the instantaneous quantum link is silent. It is a symphony of perfect correlation with no discernible melody, a secret the universe keeps even from itself until the slow, plodding speed of light allows it to be shared. This theorem is not a limitation of our technology. It is a foundational feature of reality that protects causality itself. It ensures that an effect here cannot precede a cause from a distant star, preserving the logical flow of the universe. So if this quantum door is firmly locked, where do we turn next? Perhaps the answer is not to break the speed limit on the cosmic highway, but to find a shortcut straight through the fabric of spacetime. The universe's rulebook might forbid speeding on the cosmic highway, but it says nothing about drilling a tunnel straight through. This is the promise of the wormhole, a theoretical bridge through the folded fabric of spacetime itself. In popular science fiction, these cosmic shortcuts are portrayed as shimmering gateways or tunnels of light, offering instant passage to the other side of the galaxy. But this imagery is grounded in real, albeit speculative, physics. Albert Einstein's equations of general relativity, which describe how mass and energy warp space and time, mathematically allow for such structures. They are not just science fiction, they are science possibility. The renowned physicist Kip Thorne, who rigorously explored wormholes to ensure the scientific accuracy of the film Contact, has noted that while they are mathematically permissible, their physical realization presents profound challenges. A wormhole is essentially a shortcut, a warping of spacetime that creates a tunnel or throat connecting two otherwise distant points. To visualize this, take a piece of paper and draw two dots on opposite ends. The normal distance between them is a long line across the surface. Now, fold the paper so the two dots touch. The wormhole is the tunnel that punches through the void between them, creating a path that is vastly shorter than the route along the surface. This is the essence of a spacetime shortcut. However, not all wormholes are created equal. The equations of general relativity primarily describe non-traversable wormholes, which are unstable, microscopic, and would collapse into a singularity the instant anything tried to pass through. To create a tunnel that a person, or even a single photon of light, could safely travel through, you would need a traversable wormhole. The key to keeping such a tunnel propped open against the immense force of gravity that wants to crush it shut is a substance with a truly bizarre property: exotic matter. This is not antimatter or dark matter, but a hypothetical form of matter that possesses negative energy density or negative pressure. In simple terms, it would have a kind of anti-gravity effect, pushing the walls of the wormhole apart and preventing its catastrophic collapse. The existence of such matter is allowed in certain quantum field theory contexts, like the Casimir effect, where closely spaced plates can create a region with less energy than empty space. But whether we could ever gather and manipulate it in the vast quantities needed to stabilize a macroscopic wormhole remains a monumental question. So, could we ever manipulate one of these cosmic tunnels for instant messaging across the stars? If you could somehow place the two mouths of a stable wormhole in different locations, then passing a signal through the tunnel would not break the universal speed limit from the perspective of the signal's local path. The message would simply be taking a much shorter route, yet the practical hurdles are staggering. First, you would need to find or create a wormhole, a feat far beyond our current understanding. Then you would have to move one of its mouths to a distant star system, a process that would itself be bound by the speed of light, taking centuries or millennia. Only after this immense setup could the instant communication begin. The universe, it seems, offers a potential backdoor, but the price of admission is almost inconceivably high. If the cosmic shortcuts of wormholes are too fantastical for a practical post office, perhaps the answer lies not in traveling through space, but in manipulating the very fabric it is woven from. Science fiction's iconic warp drive is no longer pure fantasy. In 1994, physicist Miguel Alcubierre proposed a mathematical model for a real starship, one that would not push through space, but would instead command space itself to move. He described the core idea as a local distortion of spacetime, creating a wave that would carry a vessel forward. The Alcubierre drive cleverly sidesteps the universal speed limit by ensuring that within its warp bubble, the ship itself is not moving at all relative to its immediate space. Instead, the fabric of the cosmos does the work. Imagine a moving walkway at an airport. You stand still on the walkway, yet you are carried forward relative to the terminal. The Alcubierre drive aims to turn spacetime itself into that moving walkway on a cosmic scale. The mechanism relies on a profound prediction of Einstein's general relativity, that mass and energy can warp spacetime. This drive would generate a warp bubble around a spacecraft. In front of the ship, spacetime would be massively compressed, pulling the destination closer. Behind the ship, spacetime would be drastically expanded, pushing the point of origin farther away. The vessel sits comfortably in a flat, undisturbed region of spacetime between these two extremes, a passenger on a wave of distorted geometry. This all sounds like the ultimate cosmic loophole, but the engineering requirements are almost incomprehensibly vast. To shape spacetime in this way requires exotic matter with negative energy density, the same bizarre substance needed to prop open a wormhole. This matter would act like a kind of anti-gravity, warping spacetime in the opposite way a planet or star does. The energy needed to create and sustain this warp bubble is another monumental hurdle. Early calculations suggested the energy equivalent of converting the entire mass of Jupiter into pure energy. Later refinements have brought that number down, but it still remains far beyond any technology we can conceive of, perhaps requiring the total energy output of a star. Yet the tantalizing possibility remains. If such a drive were ever built, it could enable missions to nearby stars in a matter of weeks or months, not millennia. The ship would glide through the galaxy on a tide of warped space, never once accelerating locally, and thus never violating relativity. So, what would this mean for communication? If we can warp a ship through space, could we warp a signal? Theoretically, a message sent from within the warp bubble would travel at the speed of light, but its journey through the compressed space in front of the vessel could mean it arrives at its interstellar destination far sooner than a beam of light traveling through normal, unwarped space. The very medium of the message's travel would be manipulated. This suggests a profound idea that the future of faster-than-light communication may not rely on breaking the rules of spacetime, but on mastering the art of bending them to our will. What if the cosmic speed limit was not a barrier at all, but merely a starting line? This is the radical proposition of tachyons, hypothetical particles born from the pure mathematics of physics that would forever travel faster than light. They are not breaking the rules of relativity, but are instead playing by a different set of rules entirely, emerging from theoretical extensions of Einstein's own equations. According to some interpretations of quantum field theory, these entities could exist in a realm where their normal state of being is superluminal. The physicist Gerald Feinberg, who coined the name tachyon from the Greek word for swift, explored how such particles could fit within a coherent, if unconventional, framework of physics. Their significance lies in how they challenge the very definition of a limit, suggesting that light speed is not an impenetrable wall, but a one-way boundary. Nothing slower can cross to the other side, but what if something was already born there? The properties of these particles are as bizarre as their proposed existence. To always move faster than light, a tachyon would need to possess what physicists call an imaginary mass. This does not mean a mass that you merely imagine, but a mathematical quantity described by the square root of a negative number. In our everyday world, this concept is abstract, but in the equations, it results in a particle that gains energy as it slows down, approaching the speed of light from above as an unattainable minimum, a perfect mirror to our own universe's unattainable maximum. This leads to profound and unsettling paradoxes, particularly for causality. If a tachyon could be used to send a signal, it could potentially arrive at a destination before it was ever sent, violating the logical sequence of cause and effect that underpins our entire understanding of reality. To make this tangible, picture the universe as defined by a light cone, a diagram representing all possible paths that light or slower objects can take from an event. We live our lives inside this cone, where causes always lie in the past and effects in the future. Tachyons, by their very nature, would exist and travel outside this cone. They would operate in realms of spacetime that are, from our perspective, causally disconnected. How then could we ever hope to detect or even use such a phantom? The challenge of proving their existence is monumental. Any tachyon emission would produce a kind of shockwave in spacetime, analogous to the sonic boom created by an aircraft breaking the sound barrier. But this would be a luminal boom as the particle dropped down to light speed. No such signature has ever been conclusively observed. Even if they did exist, harnessing them for communication seems a distant dream. How would you create a tachyon transmitter? How would you encode a message on a particle that operates by such alien rules? And most critically, how could you prevent that message from rewriting the past? The very physics that allows for their possibility may also contain the mechanisms that prevent their practical use, preserving the sanctity of cause and effect. So if particles that lie beyond light offer only paradoxes, where can we turn for a more grounded, yet equally revolutionary, approach to connecting the stars? A laser pulse strikes an opaque barrier, a wall it should never penetrate. Yet a moment later, detectors on the other side register a faint signal. Astonishingly, some part of the pulse appears to have arrived faster than a beam of light traveling the same distance through empty space. This is not science fiction, but a real laboratory phenomenon known as quantum tunneling, and its implications have sparked one of the most heated debates in modern physics. At its heart, quantum tunneling is a strange but well-established quantum mechanical effect. It allows a particle, like an electron or a photon, to pass through an energy barrier that would be completely insurmountable in the classical world. Think of it as a ball spontaneously appearing on the other side of a hill without ever having rolled over the top, a ghostly transit made possible by the probabilistic, wave-like nature of reality at the smallest scales. The controversy ignites when we examine how quickly this tunneling seems to occur. In certain meticulous experiments, particularly those involving photons tunneling through a barrier, the peak of the transmitted wave appears to emerge on the far side in less time than it would take light to cross an equal vacuum. This is often described as a superluminal group velocity, a term that refers to the speed at which the overall shape or envelope of a wave packet moves. Some researchers have pointed to these results as evidence of faster-than-light effects. Yet the broader physics community remains deeply skeptical. As one prominent researcher in the field cautions, we must be extraordinarily careful not to confuse the speed of a mathematical wave with the speed of a real physical signal. The debate hinges on a critical distinction between three different types of velocity. Phase velocity is the speed of a single wave crest, which can indeed be faster than light but carries no information. Group velocity is the speed of the wave's overall shape, which can also, in these exotic setups, appear superluminal. But the only velocity that truly matters for sending a message is the signal velocity, the speed at which the very front of a wave, its leading edge, propagates. And this signal velocity, as rigorously defined by relativity and quantum mechanics, never, ever exceeds the speed of light in a vacuum. To understand why, picture an ocean wave crashing towards the shore. You might see a particular crest surging ahead, moving faster than the wave itself is advancing. But that crest did not start the wave, It merely emerged from the complex interplay of water already in motion. The true beginning of the wave, its front, arrived earlier and moved at a slower fundamental speed. In the photonic tunneling experiments, the apparent early arrival of the pulse's peak is an illusion of reshaping. The barrier does not simply let the wave through, it filters it, absorbing the slower leading components of the wave and allowing the faster trailing parts to dominate. The peak of the pulse appears to jump forward in time, but no single photon in the pulse actually travels from start to finish faster than light. The information capacity, the true signal, is carried by the wave front, which remains stubbornly subluminal. This subtle but profound difference preserves causality. It means the universe allows for these astonishing statistical curiosities, these phantoms in the data, while still firmly forbidding any meaningful message from outrunning a beam of light. The line between perception and physical reality is incredibly fine, forcing us to ask a more fundamental question: what, in the final analysis, actually constitutes a signal? The very essence of a message comes down to a single, powerful distinction. What is the difference between seeing a pattern and actually sending one? This question was answered with revolutionary clarity by a researcher at Bell Labs, Claude Shannon, who founded the field of information theory in the middle of the 20th century. He taught us that information is not about meaning, but about the resolution of uncertainty. A true signal is not just a correlation, it is a stream of controllable, predictable data that can be used to encode a message of your choosing. As modern information theorist Dr. James Gleick explains, Shannon's work gave us the bit, the fundamental unit of data, and showed that communication is fundamentally a fight against noise. For a phenomenon to be a genuine signal, it must meet strict criteria. It must have low entropy, meaning it is predictable and non-random from the receiver's perspective. It must allow for encoding, where a sender can deliberately imprint a message onto a physical carrier. And most critically, it must be controllable. The sender must be able to force the signal to represent a 1 or a 0 at will. This is the precise point where quantum entanglement fails as a faster-than-light communication scheme. The spooky correlation is 100% real, but the outcome of any single measurement is completely random and uncontrollable. You cannot force an entangled particle to spin up to send a yes. You can only observe its random dance and later discover, through a slow, classical comparison, that your partner observed the same random steps light years away. This is why physicists distinguish between a quantum channel, which can share these mysterious correlations, and a classical channel, which is required to actually send the controllable bits that constitute a message. The capacity of any quantum channel to transmit real, controllable information is ultimately bound by the same speed of light limit that governs all classical signals. This framework of information theory is not just abstract, it is the bedrock of our modern world. It is the reason we can compress a digital photograph into a small file, and it is the principle behind the unbreakable codes of quantum key distribution. In that latter case, the entangled particles provide the perfect, random secret key, but the actual encrypted message, the signal itself, must be sent over a conventional laser or radio wave, trudging along at light speed. So, if our current definition of a signal is so firmly anchored to controllability and causality, are we perhaps missing a deeper layer of physics? Could a future theory redefine what we even consider to be information? This inevitably leads us to the final and most unyielding guardian of cosmic mail delivery, the unbreakable law of cause and effect itself. Every event in the cosmos casts a unique shadow across spacetime, a domain of influence defined by the ultimate speed limit. This structure, the light cone, is not just a diagram but the very architecture of reality. Emerging from Einstein's special relativity, It rigorously divides the universe for any given observer into three distinct regions. Within your forward light cone lies every point in spacetime you can possibly influence, your entire future. Within your backward light cone lies every event that could have possibly influenced you, your entire past. And then there is the vast region of elsewhere, points separated from you by a space-like interval. Events in this realm are utterly disconnected from your present, as no signal, no influence, not even a beam of light, could have reached you from there, nor could you yet reach them. As the philosopher of science Hugh Price has articulated, this causal structure is what gives the universe its coherent narrative, ensuring that causes reliably precede their effects for all observers. This is the inviolable rulebook of existence. Faster than light communication shatters this structure. Imagine two starships, the Odyssey and the Voyager, separated by several light years. The Odyssey sends a faster-than-light message that reads, "Do not launch the mission." According to some observers moving at high relative velocity, the Voyager could receive this warning before the Odyssey even decided to send it. The crew of the Voyager, acting on the warning, could then send their own faster-than-light message back to the Odyssey that says, "Message received, mission scrubbed." This confirmation could then arrive at the Odyssey before its captain ever pressed the send button, negating the original cause for sending the message in the first place. You are left with an effect, the scrubbed mission, that has erased its own cause. This is the notorious grandfather paradox, not confined to time travel alone, but a fundamental logical inconsistency that arises whenever information is permitted to travel outside the light cone. The mathematics of relativity enforces this division with elegant precision. The spacetime interval between two events is calculated using a formula that combines their separation in space and time. If the result is positive, the events are time-like separated, meaning one could have caused the other, and they lie within each other's light cones. If the result is negative, they are space-like separated, residing in each other's elsewhere, forever forbidden from direct causal contact. This is the universe's built-in mechanism for preserving a consistent timeline. So, would we willingly trade this foundational principle of a coherent reality for the convenience of instant messaging across the stars? The cost seems unimaginably high, plunging our understanding of history, responsibility, and even identity into chaos. Yet, the strange, probabilistic world of quantum mechanics continues to whisper from the edges of this rigid causal structure, suggesting that at the most fundamental level, the universe might not play by such simple, deterministic rules. Einstein's steadfast universe of local causality faced an insurrection from the quantum realm. This was not merely a scientific disagreement, but a fundamental clash over the nature of reality itself. On one side stood the elegant, deterministic geometry of general relativity, where influence propagates smoothly at the speed of light. On the other stood the probabilistic, fuzzy world of quantum mechanics, where particles could be in multiple places at once, and their properties remained undefined until measured. Einstein famously rejected the idea of spooky action at a distance, believing the universe must be local and real, with objects possessing definite properties independent of observation. Yet the universe, it seemed, had other plans. Quantum non-locality emerged as the battleground, a phenomenon where the measurement of one entangled particle instantly influences its partner, regardless of the physical separation between them. This is not a minor quirk, it is a feature of the quantum world confirmed by decades of rigorous experimentation. As physicist Nicholas Gisin has reflected, these quantum correlations are fundamentally non-local, yet they manage to coexist with relativity in a delicate truce. The key to this peaceful coexistence lies in a pivotal discovery from the 1960s. Physicist John Stuart Bell devised a theorem, a mathematical test that could distinguish between a universe with hidden local variables, as Einstein hoped for, and one with genuine quantum weirdness. The theorem set up an inequality, a boundary that any local hidden variable theory must obey. When scientists eventually performed the experiments, starting with Elaine Aspect's groundbreaking work in the 1980s, the results were clear and decisive. The Bell inequality was violated. The universe had chosen the quantum path, confirming that the correlations between entangled particles are indeed non-local and cannot be explained by any mechanism hidden within the particles themselves. So how does this not shatter relativity's cosmic speed limit? The distinction is exquisitely subtle. While the correlation is instantaneous, it cannot be used to send a signal. Think of it as two people, each holding one of a pair of magical coins that always land on the same face when flipped. One person flips their coin and sees heads. They know instantly with certainty that the other coin also shows heads, but they had no control over the outcome. It was a random event. The person holding the other coin just sees a random result, heads or tails, with no knowledge of whether their partner has even flipped their coin yet. This is the core of quantum non-locality, action at a distance without controllable signaling. The randomness of the individual measurement outcomes acts as a cosmic sensor, preventing any meaningful information from leaping across space. This principle is dramatically illustrated in quantum teleportation, a real-world protocol that sounds like it was lifted from science fiction. In quantum teleportation, the exact quantum state of a particle is destroyed in one location and recreated in another. This process relies crucially on a pair of entangled particles shared between the sender and receiver, yet the teleportation itself is not instantaneous. To complete the transfer, the sender must transmit the results of a measurement performed on their end over a classical, slower-than-light communication channel. Without that ordinary light-speed limited message, the receiver cannot reconstruct the original quantum state. The spooky entanglement does the heavy lifting of establishing a quantum connection, but the actual information, the signal that makes the process useful, is carried by a beam of light or a radio wave, dutifully obeying Einstein's rulebook. This careful dance between non-local correlation and local signaling forces us to ask whether our current theories are complete. Could a deeper, more fundamental framework, perhaps a theory of quantum gravity, finally resolve this century-old clash and show us a universe where these two titans are not at war, but are merely different faces of a single, unified truth? This magic ingredient, this key to unlocking cosmic shortcuts, is known as exotic matter. It is not merely rare or unknown, but fundamentally bizarre in its behavior, possessing a property that seems to defy common sense: negative energy density. The theoretical physicist Matt Visser has extensively studied the requirements for stable wormholes, noting that exotic matter is not an optional component, but an absolute necessity to prevent these spacetime tunnels from immediately collapsing. Unlike normal matter, which always has positive energy density and attracts other matter through gravity, exotic matter would theoretically possess negative energy density, generating a kind of gravitational repulsion, an anti-gravity effect. Imagine trying to build an archway out of sand. It would instantly crumble under its own weight. But if you could replace the sand with a substance that actively pushes outward, that counteracts the crushing force, the arch could stand. Exotic matter is that outward pushing substance for the architecture of spacetime itself. Its role is to prop open the throat of a wormhole, or to create the compressive and expansive regions of spacetime around an Alcubierre warp bubble. Without it, these structures are mathematically possible but physically unstable, snapping shut or failing to form in the first place. So where could such a strange substance possibly exist? We find a hint not in distant galaxies, but in the strange, empty space between two metal plates placed incredibly close together. This is the Casimir effect, a well-documented quantum phenomenon where the vacuum of space, far from being truly empty, seethes with fleeting virtual particles. When two plates are brought very near, they exclude some of the longer wavelength fluctuations, resulting in a region between them that has a lower energy density than the surrounding space. This tiny, measurable difference effectively creates a negative energy density, exactly the property we are looking for. It is a whisper of the exotic, a proof of principle that the quantum vacuum can be engineered to produce these bizarre states. The problem, of course, is one of scale. The Casimir effect produces a negative energy density so infinitesimally small it is almost beyond comprehension. To stabilize a wormhole large enough for a single proton to pass through might require negative energy equivalent to the mass of our entire solar system. For a human traversable tunnel or a macroscopic warp drive, the energy requirement could balloon to the equivalent of a galaxy's worth of mass. This is the monumental chasm between a theoretical concept and a practical technology. Yet the dream persists. One can speculate about a future civilization that has learned to mine the quantum vacuum on an industrial scale, or one that discovers a cosmological source of naturally occurring exotic matter, perhaps left over from the Big Bang. Could the dark energy that is accelerating the expansion of the universe be a vast, diffuse sea of this very substance? The questions themselves push at the boundaries of known physics, forcing us to wonder if the ultimate fuel for our faster-than-light dreams is hiding in plain sight, woven into the empty space all around us. Deep within the theoretical tapestry of the cosmos lie threads of unimaginable density, relics from the universe's first chaotic moments. These are cosmic strings, hypothetical one-dimensional objects predicted by some of our most ambitious cosmological models. They are not strings in the everyday sense, but rather, as one cosmologist describes them, cracks in the fabric of spacetime, infinitely long and thinner than a proton, yet possessing the mass of an entire mountain range compressed into every centimeter. Their existence is a direct prediction of certain grand unified theories, which suggest that as the newborn universe cooled and underwent phase transitions, flaws could have been trapped in the very structure of reality, much like cracks forming in ice. The physics of these entities is as extreme as their origin. A cosmic string would possess immense tension, a property that causes the space around it to become conical. Imagine taking a flat sheet of paper and cutting out a thin, pizza slice-shaped wedge, then taping the edges back together. The surface would no longer be flat, it would have a sharp angle. A cosmic string creates a similar distortion in spacetime itself. This warping leads to astonishing possibilities. Light or any object traveling around the string would find that multiple paths can connect 2 points, and under the right conditions, these paths could theoretically form closed time-like curves, loops in time that return to their own starting point. This is where the potential for effective faster-than-light effects emerges. If two cosmic strings were to move past each other at incredibly high relative velocities, the frame-dragging effect, the way their immense gravity pulls on the fabric of spacetime around them, could create a pathway. A signal sent on a carefully calculated trajectory around this moving configuration might arrive at its destination before a light beam traveling the normal, undistorted route between the same 2 points. From the signal's perspective, it never breaks the local speed limit. It simply takes a cosmic shortcut carved out by the string's motion. The challenges, however, are as vast as the cosmos itself. First, we have no confirmed observational evidence that cosmic strings even exist. They are predicted to be incredibly rare, perhaps with only one string residing within our entire observable universe. Second, the models that allow for these closed time-like curves often require the strings to be moving at near light speed relative to each other, a chance encounter of astronomical improbability. And finally, the stability of such a spacetime gateway is highly questionable, likely collapsing before any meaningful information could pass through. Could we ever hope to detect or even think about manipulating such a phantom? Our current telescopes search for their signatures in the cosmic microwave background or in the gravitational lensing of distant galaxies. But perhaps the real key lies not in our conventional instruments, but in a theory that remains just beyond our grasp. The ultimate answers to these cosmic riddles may be waiting within the elusive framework of quantum gravity. At the heart of modern physics lies a schism, a fundamental clash between two theories that each describe our universe with stunning accuracy, yet refuse to speak the same language. This is the quest for a theory of quantum gravity, the final missing piece in our cosmic puzzle that could redefine everything we know about space-time, causality, and the very possibility of sending a message. As theoretical physicist Carlo Rovelli suggests, we are perhaps like explorers trying to understand the ocean by studying its surface waves, completely unaware of the deeper currents and creatures below. Quantum gravity aims to plunge into those depths, to unify the smooth, geometric landscape of general relativity with the fuzzy, probabilistic world of quantum mechanics. The implications are staggering. Such a theory would not just tweak our equations, it would completely overhaul our understanding of reality at the most minute scale, the Planck length, a distance so tiny that the very concepts of space and time as we know them break down. Here, physicists propose spacetime may not be smooth and continuous. Instead, it might be granular, composed of discrete, vibrating loops or tiny, one-dimensional strings. This is the domain of quantum foam, a seething, turbulent sea of virtual wormholes and tiny spacetime bubbles popping in and out of existence. In this frenetic environment, the rigid light cones of relativity could become fuzzy and permeable. Could information hitch a ride on these fleeting fluctuations? The leading approaches to this grand unification offer tantalizing clues. Loop quantum gravity, for instance, describes space as a woven fabric of finite loops, a spin network. In this picture, the connectivity of the network could allow for non-local correlations that are more fundamental than the space-time they generate. String theory, another contender, suggests that the fundamental objects are not point particles but vibrating strings, and that their interactions across higher dimensions could create pathways for information that bypass our conventional three-dimensional space entirely. Perhaps the most mind-bending idea comes from the holographic principle, which posits that our three-dimensional universe might be a projection of information stored on a two-dimensional surface at its boundary. If this is true, then transferring information from one point to another might not require moving through the space between them at all, but could be achieved by rewriting the code on the cosmic hard drive. The experimental hurdles, however, are monumental. Probing the Planck scale directly would require a particle accelerator larger than our entire solar system. So, researchers look for indirect signatures, subtle imprints left on the cosmic microwave background, or minute discrepancies in the timing of distant pulsar signals. They are searching for the faintest whisper from a realm where gravity and quantum mechanics finally shake hands. What would it mean for communication if they succeed? It might not give us a galactic telephone, but it could reveal that information is a more primitive concept than location, that the universe is fundamentally interconnected in a way that makes our current ideas of distance and signaling seem like a temporary, local illusion. The sterile silence of a modern physics laboratory is deceptive. Within these controlled environments, a quiet rebellion is underway, as researchers design exquisitely sensitive experiments to test the ultimate speed limit. They are not building warp drives, but rather probing the edges of known physics, looking for any crack in relativity's armor. One of the most dramatic chapters in this search unfolded with the opera experiment. Scientists sent beams of neutrinos, those ghostly particles that barely interact with matter, from CERN in Switzerland through the Earth's crust to a detector in Italy, over 450 miles away. The initial results sent a shockwave through the scientific community. The data suggested the neutrinos had arrived 60 nanoseconds sooner than a beam of light would have, a tiny but monumental discrepancy. For a brief moment, it seemed a fundamental pillar of physics had cracked. Yet this is where the true strength of the scientific process reveals itself. The result was not immediately accepted as fact, but was instead met with intense global scrutiny. Other teams attempted to replicate the findings. The opera collaboration itself meticulously rechecked every aspect of their setup, from the GPS timing systems to the fiber optic cables. The culprit was eventually found, a loose cable connection and a misconfigured oscillator that had introduced a timing error. The neutrinos were, in fact, obeying the cosmic speed limit after all. This episode was not a failure, but a powerful demonstration of how science self-corrects. It highlights the immense difficulty of these measurements, where billionths of a second matter, and the absolute necessity of peer review and reproducibility. The hunt continues with even more precise methods. Laboratories now use quantum optics to study the tunneling time of individual photons. They employ atom interferometers to measure the subtle warping of spacetime with unprecedented accuracy. At facilities like LIGO, which detects gravitational waves, every anomaly in the signal is examined, not just for astrophysical sources, but for any hint that the ripples in spacetime itself might be propagating with unexpected properties. These are not wild speculations, but rigorous, incremental tests of our most fundamental theories. So what would it truly take to conclusively prove a faster-than-light phenomenon? It would require an experiment whose results are so clear, so reproducible by independent teams across the world, and so resistant to every conceivable alternative explanation that the entire framework of physics would have to be rewritten. The evidence would need to be undeniable, but if such a discovery were ever made, would we be ready for the consequences? The moment we confirm a crack in causality, we step into a realm far beyond engineering, into a universe with profoundly different rules. A universe with faster-than-light communication would force us to abandon our most cherished intuition, the steady, reliable flow of time. The very idea of a single, universal present, a shared now for all observers, is a comforting illusion shattered by relativity, and FTL would shatter it beyond repair. The philosopher Immanuel Kant argued that time is a fundamental framework through which we perceive the world, a necessary structure of the human mind itself. If that framework becomes subjective and malleable, what happens to our sense of self, to our understanding of history and the future? The physicist Stephen Hawking famously questioned the stability of such a universe, suggesting that the laws of physics seem to conspire to prevent time travel and its associated paradoxes, acting as a kind of cosmic protection for chronology. With FTL, that protection vanishes. Your now and my now would no longer be synchronized, they would be personal, local realities. A message sent from Earth could be received on a distant world in what the receiver perceives as their past, while for the sender, it is their future. This creates a cosmos without a single timeline, but a tangled web of subjective experiences where cause and effect are no longer sacred. This leads to a profound philosophical conflict between determinism and free will. If an effect can precede its cause, is the future already written? Are our choices an illusion, merely playing out in a predetermined sequence that we are experiencing out of order? Modern philosophers of physics, like Hugh Price, grapple with these questions, debating whether such a universe could possess any coherent narrative at all, or if it would descend into a kind of logical chaos where events are not anchored to a stable past or future. The ethical implications are staggering. Instantaneous interstellar diplomacy sounds ideal, until you consider that a misunderstanding could escalate into a galactic conflict in the blink of an eye, with no time for reflection or de-escalation. A peace treaty could be signed and broken before the ink, metaphorically speaking, had even dried in one reference frame. Consider a thought experiment where a historian on Earth uses an FTL device to send a warning back in time to prevent a catastrophic interstellar war. The message is received, the war is averted, and history is rewritten. But in this new, peaceful timeline, what motivation would the historian have to send the warning in the first place? The act of sending the message erases the very reason for its own existence, creating a paradox that unravels the logical consistency of reality. This interplay between metaphysics and empirical science is not merely academic. It strikes at the heart of what it means for the universe to be intelligible and lawful. Science fiction has long served as our collective testing ground for these ideas, from the causality loops in films like Arrival to the temporal conflicts in Doctor Who, exploring the human cost of tampering with time. These stories force us to ask a crucial question: is a power that allows us to connect the stars worth the price of a coherent reality? The answer may depend on whether we value connection over causality, and whether we believe humanity is mature enough to handle a technology that does not just cross space but rewrites history itself. The glowing blue tunnel of a starship's warp jump is a cinematic promise of instant travel, yet this iconic image conceals a brutal negotiation with physics. Science fiction, from the hyperdrives of Star Wars to the instantaneous ansibles of Ursula K. Le Guin, presents faster than light travel as a solved engineering problem, a tool for telling human stories across a galactic stage. Science fact, however, imposes a far steeper price. As astrophysicist Neil deGrasse Tyson often emphasizes, the value of science fiction lies not in its accuracy, but in its capacity to ignite the imagination of those who will one day do the real science. It asks the initial, daring what if, while physics demands the rigorous how. The hyperdrive typically handwaves the universe's energy demands, treating a journey across 100,000 light-years as a simple matter of fuel, not a fundamental rewriting of local spacetime. An ansible, a device for instantaneous communication, conveniently sidesteps the causal paradoxes that would shatter the logical sequence of events, presenting a universe where information is free from the tyranny of light speed. These creative liberties are not failures, they are narrative necessities, but when we dissect them, we find a fascinating dialogue between fantasy and theory. The warp drive from Star Trek, for instance, finds a startling parallel in the Alcubierre metric. Both concepts involve warping space to move a vessel, but where the television show uses the elegant technobabble of dilithium crystals, the real-world equations demand monstrous quantities of exotic matter with negative energy, a substance that may not even be possible to gather in such amounts. This is the consistent pattern. Fiction provides the dream, and physics reveals the daunting invoice. Sometimes, however, the inspiration flows both ways. The spooky action at a distance that so troubled Einstein has become a staple of quantum science fiction, long before laboratories proved entanglement was real. The fiction anticipated the bizarre principle, while the science revealed why we cannot use it for a subspace radio. This creative synergy forces a critical question: How can we foster science fiction that inspires ambition without misleading about the monumental challenges? A story that glosses over the cosmic speed limit might be thrilling, but one that wrestles with its implications, that shows the human cost of causality violation or the societal upheaval of true instantaneous connection, could prepare us for a future where the very fabric of reality is our engineering material. If such a technology ever moved from the page into our world, its impact would ripple far beyond physics, reshaping everything from our concept of self to the foundations of our interstellar communities. The first faster-than-light message sent to a distant colony would not be a simple hello, but a seismic event reshaping human civilization from the ground up. Picture a world where a trade deal negotiated with a society orbiting a star 50 light-years away is settled in the time it takes to drink a cup of coffee, where a medical breakthrough discovered on a research station in the Orion Nebula is implemented in hospitals on Earth moments later. This is the promise of instantaneous interstellar contact, a future where the very concept of distance is rendered obsolete. Futurists speculate that such a capability would trigger shifts as profound as the invention of the printing press or the internet, but on a cosmic scale. The global economy would transform into a truly interstellar one. Financial markets would operate with perfect information across solar systems, creating unparalleled stability or, conversely, enabling catastrophic, instantaneous crashes that ripple across worlds. The sociologist Dr. Alondra Nelson has explored how communication technologies reshape social bonds, suggesting that FTL could forge a galactic community, a unified human identity that transcends planetary origins. Cultural exchange would explode. You could experience the art, music, and stories of an alien civilization, not as a historical relic from centuries past, but as a living, breathing dialogue. Education would become a universal and simultaneous awakening, with students on Mars attending a lecture given in real time by the leading expert on a planet in the Alpha Centauri system. Yet this hyper-connected galaxy would also be incredibly fragile. The same channel that carries a peace treaty could also carry a weapon of mass disruption. Misinformation and propaganda, a challenge on our own planet, would become an interstellar plague, capable of igniting conflicts between stars before any slower-than-light fact-checking could intervene. Political systems built on the slow deliberation of regional representatives could be destabilized by the demand for instant galactic consensus. On a deeply personal level, the human experience of distance and longing would vanish. The emotional ache of being separated from loved ones by years of communication lag would be a forgotten relic of a slower age. Relationships could be maintained across light years as effortlessly as a video call across a city, fundamentally altering our sense of home and connection. This is analogous to the Internet's impact, but magnified to an almost unimaginable degree. If the Internet compressed our world into a global village, FTL communication would compress the galaxy into a single, bustling city square. The risks would be equally magnified. Imagine the first FTL message arriving not from us, but from someone else. That single transmission containing a greeting, a warning, or simply an uninterpretable data stream would force humanity to confront its place in the cosmos in an instant. The technological requirements for such a system are as monumental as the societal changes it would bring, demanding a fundamental re-engineering of reality itself. Stabilizing a wormhole demands more energy than our sun will release in its entire lifetime. This is the first and most brutal engineering nightmare confronting any attempt to build a faster-than-light communication device. Theoretical physicist Lawrence Krauss has bluntly stated that the energy scales involved are not just beyond our current technology, they are beyond the scope of human civilization as we know it. To generate a stable, traversable wormhole just 1 meter in diameter might require negative energy equivalent to the mass of Jupiter. A macroscopic gateway for a spacecraft would need the energy equivalent of a galaxy, concentrated and manipulated with impossible precision. The material science is equally daunting. The exotic matter needed to prop open the wormhole throat is not something we can mine or manufacture in a lab, at least not in any meaningful quantity. While the Casimir effect demonstrates the principle of negative energy density, the amount produced is so infinitesimally small, it is like trying to power a city with the static electricity from a single sock pulled from a dryer. We would need to find a way to amplify this quantum whisper into a cosmic shout. Even if we solved the power and material problems, we face the challenge of control. A warp field for an Alcubierre drive would need to be perfectly shaped and maintained. Any fluctuation, any tiny imperfection in the field geometry could have catastrophic consequences, potentially unleashing unimaginable energies that would vaporize the ship and everything around it. The system would have to be flawless, operating with a stability that defies the chaotic nature of quantum fields. For entanglement-based communication, the primary hurdle is quantum decoherence. Keeping a pair of particles entangled over interstellar distances is like trying to keep two perfectly synchronized clocks in different cities, while every passing photon, every stray gravitational wave, and every vibration of the universe itself tries to desynchronize them. The particles are exquisitely sensitive to their environment, and over light years, that environment is impossibly noisy. We would need a way to perfectly shield them from the entire universe, a feat that seems to contradict the very nature of quantum interaction. How would such a system even connect to our existing world? Integrating an FTL network with the Internet presents its own labyrinth of problems. The protocols that govern data packets today assume lightspeed delays. An instantaneous signal would break those protocols, requiring a complete overhaul of the global network's fundamental architecture. A hypothetical blueprint for an FTL transceiver would highlight vast, empty sections labeled unknown physics. It would show containment vessels for energies we cannot produce, shielding for phenomena we do not understand, and control systems for stabilizing geometries that are mathematically possible but physically unstable. The gaps are not merely technological, they are foundational. So, are these hurdles fundamentally insurmountable? Or could the relentless, exponential progress of artificial intelligence and automation eventually crack a problem that seems to require the resources of a god? Artificial intelligence is now scanning the equations of general relativity, searching for patterns no human mind could ever perceive. This is not a replacement for human genius, but a powerful new partner in tackling physics' most profound puzzles. At research institutes around the world, machine learning algorithms are being fed decades of cosmological data and theoretical models, tasked with a single overarching goal: to find stable configurations for wormholes or to optimize the impossible energy requirements of a warp drive. These systems excel in domains where human intuition fails, navigating vast mathematical landscapes with billions of parameters. In one notable case, an AI analyzing the complex stability equations for a hypothetical wormhole identified a previously overlooked class of solutions that required slightly less exotic matter, a tiny but meaningful step forward. The advantage is sheer scale and speed. Where a physicist might test a handful of model variations in a week, an AI can run millions of simulations, exploring the entire possibility space and highlighting the most promising avenues for further human investigation. This is accelerating the entire research cycle, turning years of calculation into days of computation. The applications are remarkably concrete. For quantum communication, AI systems are designing intricate quantum circuits that can maintain entanglement between particles for longer durations, pushing against the relentless decoherence that plagues such systems. In cosmology, automated telescopes sift through petabytes of sky survey data, hunting for the faint, telltale gravitational lensing signatures that might betray the presence of a cosmic string. These are not science projects, they are active research tools leading to tangible, if incremental, progress. Yet these powerful tools have clear limitations. An AI can find a correlation, but it cannot yet explain the underlying physical principle. It might output a set of parameters that mathematically describe a stable wormhole, but it cannot tell us if that configuration violates a deeper law of quantum gravity we have yet to discover. The output still requires deep human interpretation, a collaboration between silicon speed and carbon-based insight. The ultimate promise lies in a future where AI moves beyond optimization and into genuine discovery. Could an advanced learning system trained on the entirety of known physics propose a completely unforeseen mechanism for faster-than-light travel, one that sidesteps our current conceptual roadblocks entirely? We see glimpses of this potential in other fields. In particle physics, AI algorithms analyzing data from the Large Hadron Collider have already helped identify rare particle decay patterns, and in drug discovery, they routinely generate molecular structures with desired properties. This democratizing power of AI could reshape who gets to participate in this cosmic quest. Open-source code and shared datasets allow small university teams or even dedicated amateurs to contribute to the search, breaking down the barriers imposed by billion-dollar laboratory budgets. This naturally leads to a broader, more inclusive effort where the next great leap might come from anywhere on Earth, fueled by a global collaboration as interconnected as the universe it seeks to understand. The search for a cosmic post office cannot be the work of a single nation or a solitary genius. It demands a global alliance of minds, a unified scientific front reminiscent of the International Space Station, where former rivals now collaborate in orbit. The Director General of CERN has often remarked that their greatest discovery is not a particle, but the very model of international cooperation itself. This same spirit is essential for faster-than-light research, a field so vast it requires the combined intellect of physicists, engineers, computer scientists, and cosmologists, all sharing data and inspiration across continents. The monumental discovery of the Higgs boson was only possible because thousands of researchers from over 100 countries pooled their resources and expertise for decades. This model of shared purpose, where a breakthrough in a lab in Tokyo can instantly inform an experiment in Buenos Aires, dramatically accelerates the entire pace of discovery. Open science platforms and preprint archives ensure that new theories are stress-tested by the global community from the moment they are proposed, creating a living, breathing conversation that pushes knowledge forward. Yet this collaborative dream faces real-world hurdles. How does a consortium of nations decide which FTL concept deserves billions in funding? Who holds the intellectual property for a discovery that could redefine human civilization? These are not merely scientific questions, but profound tests of our ability to govern shared ambition. One can envision a future international warp physics consortium, with member states contributing not funds, but dedicated resources, supercomputing time, or access to unique facilities like deep space neutrino detectors. The challenge lies in creating incentives that align national interests with the collective good of humanity, ensuring that every participant feels their contribution is valued and that the rewards of success, should it ever come, are shared equitably. This leads to a deeper question: what ethical frameworks must we build to ensure that a power capable of connecting stars is developed with wisdom and foresight for all? A signal from the void arrives not as a whisper, but as a command to redefine our place in the cosmos. What if the first faster-than-light message we receive is not from ourselves, but from another civilization entirely? This single question moves the challenge from physics to philosophy, demanding an ethical framework before the technology even exists. Dr. Maria Pozas, a scholar of space ethics, argues that we must build our moral compass for such technologies before they are in our hands, not in the frantic aftermath of their arrival. The development of FTL communication cannot be a purely technical pursuit. It must be guided by principles drawn from bioethics, international space law, and our own difficult history with disruptive innovations. The core risk is an uncontrolled technological leap, one that grants immense power without the wisdom to wield it responsibly. We have seen this narrative before, from the dawn of nuclear fission to the rise of artificial intelligence, where the capacity for both creation and destruction arrived in the same package. The foundational principles for FTL must be established now. A primary pillar is the preservation of causality, treating the logical flow of time not as an obstacle to be overcome, but as a sacred feature of a coherent universe to be protected at all costs. Any protocol must rigorously prevent the creation of paradoxes that could unravel the fabric of cause and effect. A second pillar is universal and equitable access, ensuring that such a transformative technology does not become the exclusive tool of a single corporation or nation-state, creating an unbridgeable chasm between the connected and the isolated. We must also consider the environmental footprint of FTL systems, which likely require energies capable of reshaping local spacetime, posing risks we cannot yet fully calculate. The ethical dilemmas become starkly practical. Could FTL be weaponized not with projectiles but with information, by sending a destructive data stream that collapses a distant society's financial or digital infrastructure instantaneously? What about FTL surveillance, where a probe could observe any point in the galaxy in real time, erasing any concept of privacy on an interstellar scale? Navigating these questions requires more than closed-door meetings among experts. It demands robust public engagement and transparent global governance. Who should decide the rules for a technology that affects all of humanity? The answer must involve a diverse chorus of voices, from scientists and engineers to philosophers, artists, and everyday citizens, all contributing to a collective vision for our future among the stars. The stakes are nothing less than the character of our interstellar civilization. Will we be a species that connects with wisdom, or one that communicates with chaos? This ethical groundwork naturally leads to the next critical layer, the complex web of laws and regulations needed to turn these principles into enforceable practice. The first faster-than-light communication treaty would not be written by scientists, but by teams of international lawyers working in windowless rooms. Their challenge is unprecedented, drafting laws for a technology that fundamentally alters our relationship with distance and time. Existing frameworks like the Outer Space Treaty, which declares space the province of all humankind, provide a starting point, but they are utterly unprepared for the legal chaos of instantaneous information. A message transmitted from a corporate station in lunar orbit to a private vessel near Alpha Centauri immediately raises jurisdictional nightmares. Which nation's laws govern the content of that transmission, and who holds the authority to prosecute a violation? Space law experts point to the need for a new legal paradigm, one based on the principle of destination jurisdiction, where the laws of the receiving entity's location apply, regardless of the signal's point of origin. This alone would require a complete rewriting of international communication law. To oversee this new frontier, a regulatory body would need to be established, perhaps an International FTL Communication Authority, or IFCA. Its composition would be a diplomatic minefield, requiring representation from every spacefaring nation, as well as neutral scientific and ethical advisors. Its mandate would be immense, covering everything from technical standards and bandwidth allocation to the prevention of weaponization. Enforcement is the most daunting task. How do you penalize an entity that can transmit information from a hidden base in the Kuiper Belt? The threat of being disconnected from the FTL network might be the only viable deterrent, a digital exile with profound economic and social consequences. Intellectual property disputes would reach cosmic proportions. If a research consortium develops a new FTL protocol, does their patent apply across all human-settled systems? The legal battle over the first FTL compression algorithm could dwarf all terrestrial copyright conflicts combined. Liability presents another terrifying frontier. If a careless FTL transmission creates a causality paradox, damaging the integrity of a local timeline, who is held responsible? Can there even be legal liability for unraveling cause and effect? Data privacy becomes almost meaningless when a transmission can be intercepted anywhere along its non-local path, requiring a new form of quantum encryption that itself would need global regulation. The United Nations Committee on the Peaceful Uses of Outer Space would likely become the central arena for negotiating these treaties, a process as complex and fragile as the physics behind the technology itself. Consider a hypothetical case where a fast-moving colony ship using an Alcubierre drive receives an FTL stock market tip from Earth. Acting on this information, they make a trade that destabilizes the economy of a Martian settlement. The Martians sue for damages, but the colony ship argues they were outside the jurisdiction of any planetary government when they received the signal. This single case could tie up interstellar courts for decades. The core dilemma is whether our legal systems, which evolve slowly through precedent, can possibly keep pace with a technology that redefines reality itself. This gap between innovation and governance creates a dangerous vacuum, one that can only be filled by an informed and engaged global public, demanding that the rules for our connected future are written with wisdom and foresight for all. The equations for warp drives remain abstract symbols until we translate them into a shared language of understanding. Making the profound complexities of faster-than-light physics accessible is not about dumbing down the science, but about building bridges of intuition for everyone. As science educator and communicator Dr. Alam Shah often emphasizes, the goal is not to make everyone a physicist, but to empower people with the fundamental ideas that shape our universe. This public science literacy is the bedrock upon which we can have informed, democratic conversations about technologies as transformative as FTL communication, discussions that will ultimately shape the ethical and legal frameworks governing their use. The most effective tools in this endeavor are metaphor and visualization. Instead of presenting the complex tensor calculus of general relativity, we can describe spacetime as a flexible rubber sheet and a warp bubble as a surfer riding a wave contracted in front and expanded behind. Interactive museum exhibits allow visitors to virtually manipulate these cosmic fabrics, feeling the conceptual weight of negative energy and exotic matter. Social media campaigns use short, compelling animations to illustrate why quantum entanglement cannot send a message, perhaps showing two dancers whose moves are mysteriously linked, yet whose performance remains an unpredictable, random ballet to any audience member. Documentaries bring the human drama of the scientific quest to the forefront, showcasing the researchers working at the edge of possibility and the immense challenges they face. A masterclass in this public engagement was the global release of the first ever image of a black hole by the Event Horizon Telescope collaboration. They transformed an esoteric mathematical singularity into a tangible, almost visceral visual experience that captivated the world. It was not just a picture, it was a gateway to discussing gravity, light, and the very nature of space and time. This model of open collaboration and stunning presentation provides a blueprint for how a future breakthrough in FTL physics could be shared. We must proactively dismantle common misconceptions, such as the persistent belief that quantum entanglement is a form of cosmic instant messaging. Clear explanations focus on the difference between correlation and control, emphasizing that the randomness of quantum outcomes acts as a built-in cosmic sensor. Museums, schools, and digital platforms are the front line in this effort. Planetarium shows can transport audiences on a journey through a visualized wormhole, while online courses can deconstruct the principles of the Alcubierre drive for curious learners of all ages. The objective is to create a society that is not a passive recipient of technological revelation, but an active, engaged participant in its narrative. Each person who grasps these concepts becomes an ambassador for rational inquiry, capable of critically evaluating claims and contributing to the vital public discourse. This groundswell of understanding is what will ultimately guide the future directions of FTL research, ensuring it progresses not in an isolated lab, but under the thoughtful gaze of an enlightened and curious humanity. The next decade of physics will be defined by a new generation of tools designed to probe the universe's deepest layers. Massive gravitational wave observatories, like the planned Laser Interferometer Space Antenna, will listen for the faint ripples from cosmic strings or the birth of microscopic wormholes, phenomena that current technology cannot detect. On the quantum front, increasingly powerful quantum computers are being used to simulate the behavior of exotic matter or model the stability of warp field geometries, tasks that are impossible for classical computers. These are not isolated efforts but part of a coordinated push to find empirical evidence where once there was only theory. Leading researchers suggest that while a functional warp drive remains centuries away, the first experimental hints of a stable wormhole configuration or a new quantum gravity effect could emerge within the next 20 to 30 years. The James Webb Space Telescope contributes to this quest indirectly by peering back to the universe's infancy and studying the fundamental constants of nature. Any tiny variation in these constants over cosmic time could signal a crack in our current models, a place where the rules of spacetime itself might be more flexible than we thought. Concurrently, advances in materials science are creating metamaterials with engineered optical properties that can mimic the warping of spacetime in a lab, allowing us to test the principles of an Alcubierre drive on a tabletop scale. The energy barrier, once thought to require the mass of Jupiter, is being chipped away by theoretical refinements that suggest more efficient warp field shapes or novel ways to source negative energy from the quantum vacuum. This entire endeavor is becoming profoundly multidisciplinary. Insights from computer science are helping us manage the immense datasets from cosmological surveys, while principles from biology are inspiring resilient, self-healing network designs for future quantum communication arrays. Scientific consortia like the Breakthrough Initiatives have published roadmaps that include dedicated searches for any astronomical anomalies that could be signatures of advanced propulsion or communication technologies, treating the cosmos itself as a laboratory for discovery. The first sign of a genuine faster-than-light phenomenon would likely be incredibly subtle, perhaps a statistical anomaly in the arrival times of neutrinos from a supernova or an unexpected correlation in a quantum entanglement experiment over a planetary distance. It would not be a blinking light on a console, but a faint whisper in the data that, upon verification, forces us to redraw our maps of reality. How can you witness this unfolding journey? The same open science platforms that researchers use are available to the public, offering a front-row seat to the greatest detective story in the cosmos. The equations of faster-than-light physics are not carved in stone, but written in the language of ongoing discovery, a conversation you can join right now. Your journey into this fascinating frontier does not have to end here, as a wealth of resources exists to bring you to the very edge of known science. For those who want to go beyond casual interest, peer-reviewed journals like Physical Review Letters and Nature Physics publish the groundbreaking papers, but their dense format can be intimidating. A more accessible entry point is through expert-led platforms like rziv.org, a free online repository where physicists post their latest research before formal publication, offering an unfiltered look at the ideas shaping our future. To truly build your understanding, consider structured online courses from institutions like MIT OpenCourseWare or edX, which provide free lectures on relativity and quantum mechanics from world-class professors. Many working physicists also recommend specific books to bridge the gap between pop science and textbook rigor. Titles like Kip Thorne's Black Holes and Time Warps or Carlo, Ravelli's The Order of Time offer profound insights with poetic clarity, while podcasts such as The Joy of Why with Steven Strogatz or Daniel and Jorge explain the universe break down complex concepts during your daily commute. As you explore, developing a critical eye is your most valuable tool. Distinguishing between peer-reviewed science and exciting speculation is crucial. A peer-reviewed paper has been scrutinized by independent experts, while a provocative article on a popular science website, though often based on real research, may extrapolate far beyond the evidence. Look for citations, check the author's credentials, and be wary of claims that promise revolutionary technologies without acknowledging the immense, unresolved challenges. Engaging with the community can transform your learning from a solitary pursuit into a collaborative adventure. Online forums like the Physics Stack Exchange allow you to ask specific questions and get answers from knowledgeable enthusiasts and professionals. Social media groups dedicated to cosmology or quantum gravity are vibrant spaces for discussion, and even major conferences often stream their key talks publicly, letting you sit in on the debates defining the field. The story of science is filled with contributions from dedicated amateurs, from individuals who analyze public data from space telescopes to identify exotic celestial objects, to programmers who help model complex systems through distributed computing projects. Supporting this entire ecosystem is the bedrock of public funding for basic research and science education. Writing to representatives, advocating for STEM programs in schools, and donating to organizations that promote scientific literacy are all ways to ensure the next generation has the tools to continue this quest. The greatest resource, however, is your own persistent curiosity. Keep questioning, keep exploring, and remember that every profound truth in science began as a question in someone's mind, no different from your own. Our exploration reveals a cosmos governed by elegant, unyielding laws. The dream of faster-than-light communication remains just that for now, a powerful idea that physics gently but firmly resists. From the spooky links of quantum entanglement, which cannot carry a whisper of a message, to the cosmic tunnels of wormholes, which demand energies beyond our grasp, the universe consistently protects its ultimate speed limit. These are not dead ends, but invitations to think more deeply. The very act of confronting these boundaries has expanded our understanding of spacetime, information, and causality itself, revealing a reality far richer and more interconnected than we ever imagined. This journey underscores a beautiful truth about science. Its greatest progress often begins not with an answer, but with a profound and stubborn question. Our drive to connect across the stars forces us to invent, to question, and to dream. As the visionary Carl Sagan once reflected, somewhere, something incredible is waiting to be known. That incredible something might be a new particle, a new equation, or a new way of seeing the cosmos that brings the stars within reach. The future of this quest is unwritten, and your curiosity is a vital part of it. What possibilities do you find most compelling? Share your thoughts and questions in the comments below and join a community of explorers. For more deep dives into the mysteries of the universe, be sure to subscribe. The next great discovery could be